Boom. Okay. So where we start out with Arian welcoming everyone. Hey, Kids Math here. And we watched our videos. And we pick up with vaporization. Today's a lot about phase changes, which is a pretty good one. Vaporization, also known as evaporation. This is just going to be the change from liquid to a vapor. Exothermic, endothermic. Got a 50-50. I got an endo out of that kid. Exo, endo. What do you like? Is that an endo? Yeah. Yep, this is endo, kids. Come on, think about it. We're going from a liquid up to a vapor. You're going to have to put energy into that. So this is always going to be an endothermic. With that, we're going to bring back our friend delta H VAP and make sure we understand that term. Delta H VAP is the energy needed to convert 1 mole of liquid to a vapor, and we're going to have to categorize that at standard atmosphere. At 1 ATM, at a standard atmosphere, so that we're not changing the pressure. Okay, and what did we need to remember with our HVAP? Remember, bigger IMFs, directly proportional, bigger HVAP. It's going to be harder to get something to vaporize. Don't, pardon? Yeah, because that was the whole, it's endothermic. So we got to put energy into it. This is always going to be a positive energy. It's always going to be directly proportional to the IMFs. So we like that. So your book and every other book has this chart in it. Here's your vapor pressure chart. And here's how it's referred to. Notice we've got a nice line here at 760. So that's going to be normal boiling point. So these are 3 different substances. What we have is diethyl ether, which we don't know anything about. Pardon? Can I? Page 417. Yeah. But it's your vapor pressure chart. It's not really worth copying too much verbatim. It's more the interpretation. What we're looking for is diethyl ether is going to be relatively nonpolar. Ethanol is not only polar, but it's got 1 hydrogen bond. And water, we know, is very polar with 2 hydrogen bonds. So that explains why water is further skewed to the right, because what that means is stronger IMFs. That's going to decrease the vapor pressure. So we're going to have to increase the temperature to get the vapor pressure up to where the vapor pressure equals the atmospheric pressure, which is right there, 760. This is going to be our normal standard pressure. So just know that your nonpolar things are going to be further to the left, meaning it's going to take them. Let's get a nice, can I zoom back out a little bit? Get rid of him. But what we can say is nonpolar have very weak IMFs. So they already have a head start on vaporizing. They already have a high vapor pressure. So it takes low temp to reach atmospheric pressure and boil. These are the kind of sentences that we want to put together to explain. We're linking bonding, nonpolar bonding molecule to intermolecular forces to a physical change. This is the thread we're trying to weave with our sentences. Don't just regurgitate a fact, but put that fact into perspective of how that affects the IMFs to the vapor pressure. And of course, the other side of that's going to be the hydrogen bonding, very polar, very strong IMFs, holding it in the liquid phase. So it's harder to get the vapor pressure going. And the analogies that I use, water is the best strong IMF I can come up with. The weak IMF I come up with is acetone fingernail polish remover. You open that up, you leave that, poof, it's gone. Okay, alcohols do the same, just not as much, because alcohols are still going to have some intermolecular forces. So does vapor pressure make sense? Good. It's one of those common things. The most commonly misused answer in high school chemistry is vacuum. Why did something happen? Oh, it was a vacuum. Vacuums are very rare. They're not common. It's not why things happen. The second one is vapor pressure. Why did something happen? It's vapor pressure. And everything has vapor pressure. It's the pressure of that gas above a liquid anytime. And it's always going to be in dynamic equilibrium. In this case, where you're comparing the boiling points of 3 different substances due to their molecular structure. Yes. You use vapor pressure when the problem asks you about boiling point. Because boiling is simply pressure. That's all it is. Matter of fact, that's a good little transition. Boiling, we defined the other day. That's when vapor pressure equals atmospheric pressure. So if we do a little brief thingy, let's look at kinetic energy and boiling. Two graphs. Number of molecules. Kinetic energy. Same. The lines are different. So what's the variable that we're changing here? Close, the other one. Because if we try to compare two different things boiling, that's going to be weird because we just did that. See, the molar mass and the atomic structure, that's what we're explaining here. This one is a temperature graph. Yep. So this one's happening at low temp. We talked about these distribution graphs. These are called Maxwell Boltzmann distribution graphs. We did these when we did gas laws. And what we're saying is at low temperature, there are more molecules that have the same amount of energy. At a higher temperature, the molecular distribution is spread out. And to be honest with you guys, these should both have the same area under the curve. I don't know how close I am, but I'm trying to get them to be about the same area under the curve. No, these are the same. Pick a compound. Let's do ethyl alcohol. These are ethyl alcohol at low temperature, ethyl alcohol at high temperature. Why is it what? Because at lower temperature, more molecules are going to have the same amount of energy, and it's going to be a lower amount of kinetic energy because the fifth postulate of Dalton's atomic theory or of gases is that kinetic energy is directly proportional to temperature. And so if they're at a lower temperature, they're going to have that kinetic energy. Now, the part I'm leaving off is the important one, which is right here. This little line right there. And if we make it, huh? It doesn't. I'm just changing the distribution. That's why I say the area under the curve should be the same.
And so it's saying like as if there's molecules, you're not actually changing the number of molecules or the kinetic energy, it's just saying with this many of the molecules.
I think I agree with him. So that line, that kinetic energy line, these are molecules with energy needed, energy to overcome their intermolecular force. And once they overcome their intermolecular force, that's going to increase the vapor pressure. And what's the end result of increasing the vapor pressure?
Yeah.
Boiling. Thank you. So at a higher temperature, things have more molecules are going to have that distribution, bigger area under the curve at a higher temperature, because there are more molecules that have enough energy to overcome and break out of that liquid phase and to boil. So boiling is where vapor pressure equals atmospheric pressure. Well, guess what? If you go up in altitude, you decrease the pressure. Everest doesn't count because, well, nobody goes there. But think about as we go up, and you love the typo. Look at that. I'm writing the publisher. Huh? You can't say that anymore. Mount McKinley is Denali. meaning the high one. So as we go up in altitude, our pressure goes down. Look what happens to our boiling point. Water boils at 80 degrees Celsius. That's still hot, but 20 degrees less. Compare that to Death Valley that's slightly below sea level, and it's going to boil above 100. So what's the takeaway? As we increase our altitude, we decrease our pressure. And when we decrease our pressure, we decrease our boiling point. So increase altitude. Decrease pressure, which makes vapor pressure equal atmospheric pressure easier. So lower boiling points.
But like, I'm just thinking that it's like, we're like on the mountain, and it's like really cold. How would you boil something?
See, no, it's quite the opposite problem. When you're up at high altitude, things boil so easily that it takes longer to get your food to cook. Uh-huh. Yeah, that's because your pressure is so low.
Wait, why? Why? Like, is that something that's a boiling point?
Yeah, but it's boiling at a lower temperature then. So things are boiling, but they're not cooking as fast,
Oh, okay. So there's
right?
little bubbles, but it's not.
So it's boiling, but it's boiling at 80 instead of boiling at 100. So you're going to have to cook it longer at 80 than you will at 100
And that's just because of like the.
because of the pressure. Because boiling is all about pressure. Okay. And you know, I don't want to self-gloss, but I've kind of been to every one of these except one. And I strongly recommend it, including Madison, Wisconsin. Huh? I have not. I have not. I'm close. I've got about 10 left. What? That's nice, Mike. Bing. Whoa, is that a page? Well, that's a page. This is called a phase diagram. Not to be confused with a phase change diagram that we're going to do in a minute. What a phase diagram does is what we've been doing all morning. This relates pressure and temperature to state of matter. This is a phase diagram for water. You'll always be able to recognize water. It's one of about 6 different substances that has a negative slope to this line. Most other ones will have a positive slope to that line. Water is very unique. We already know that, right? Here's one of the ways that water is unique. Suppose you were in a fixed temperature environment and I gave you a block of ice and I said, make some of it melt. How would you do it? You're in a fixed temperature environment.
Like, can you put stuff around? Blow dryer.
Look, where would you temperature?
You guys are really bad at this game.
Yeah, yeah.
Let me come at this from another direction because you're failing miserably.
Yeah, put more like something on it.
What happens? I know we're in Florida, but how come people can ice skate other than they have phenomenal balance and all that stuff? But what lets ice skates skate?
They pierce the ice.
So if I take a big knife and I push it down on my countertop, is my knife going to skate?
No.
No, it won't.
Oh, there, it's not.
No,
sharp. It's
it
like-
will
it's
not.
smooth. It's like a knife, like a butter knife.
Because water's unique. When you put pressure on water, it melts. Not everything does that, but water does. And it also attributes to this negative slope on this line. How come? Because what makes water different than everything else, kids?
When you put pressure on water, it melts. Yeah.
But that's the end result because of the structure of the hydrogen bonds. What do the hydrogen bonds do?
Because they're polar and hydrogen is so tiny.
Whoa. You're doing good there for a while.
Like the bonds like separate more, right?
I am making a very, very strong concerted effort to give you these sentences, these words of explanation. Please give them back to me on the test. Don't just regurgitate a fact. So water's different because its solid is less dense than its liquid because the liquid has hydrogen bonds going on. So as soon as it starts to liquefy, the hydrogen bonds pull the liquid closer together. When something freezes, you have to break those hydrogen bonds apart, increasing the volume. That makes the ice float. Water's very, very rare in that case
Why is it because of the liquid bonds? What's
because of the hydrogen bonds. Hydrogen bonds can exist in the liquid. They don't really exist in the solid. To make ice a solid, we have to create that crystal lattice that we've talked about, the regular repeating arrangement. So to make a solid, you say, okay, you go over there, you go over there, you go over there, you go over here, and that spreads the volume apart. So you increase the volume, that decreases the density, and ice floats. The solid is less dense than the liquid. That's really, really unusual. And it's probably one of the keys to life, because if it didn't, think of things that again, we're Florida, I'm sorry, but lakes and oceans and things would freeze from the bottom to the top. Aquatic life would die. We would never crawl out of the primordial ooze. Sorry, kids. Good news, we did. Pressure. So water's different here. There's one difference. The other one is pressure melts water. Now think about it before. What is the pressure doing that's going to make that water melt? Think. You've already answered enough. Let Kyan have a turn. Stop staring. Makes you nervous. What does pressure do that makes the water melt? What does it do? What does it do? What does it do? Remember, to make the ice, to make the solid, we had to move everybody apart. You get over here, you get over here, you get over here. We had to move everybody. All of a sudden, you pressurized it, boom. You broke the hydrogen bonds.
You broke them? I thought you made them when you become. Yeah.
No. Well, you're allowing them to happen. You broke the crystal lattice,
Yeah.
and you're allowing the hydrogen bonds to take effect. Okay?
Solid to liquid.
Okay. That went good. Interpretation of the graph is pretty common. Pressure will always be on the Y, temperature always on the X. You'll know it's water because it has a negative slope. If it's not water, a traditional, whoops. I think I have another one in here, but if it's not water, it's still going to come up, but it's going to have a positive slope. It's still always going to go in the form of solid, liquid to gas as you go around the clock dial.
Oh, you ever have to figure out what it is?
Yes. So they'll give you the graph. And that's what we're working towards. So solid, liquid, gas, but we have a few points we have to define here first. The point on the graph where three lines intersect has got to be important. And that is the triple point. Mikey, what's the triple point?
The triple point is where
Thanks, Mikey. It's where all three lines meet. It's coexistence. All three are happening at the same time. Okay, just a little latitude, people. We're recording this, for heaven's sakes. This is going to be permanent record. Okay, they totally know it's you, Neha, because we're showing you out. How do we imagine triple point? Okay, close your eyes. Imagine you're in Colorado. You're in a nice mountain pass. There's snow on the ground, fresh blanket of white snow, and off to the distance on your right-hand side, there's a little lake. And that lake has a little bit of water vapor coming off of it as the sun bounces off of the surface and reflects. That's triple point, kids. You've got solid snow, you have liquid pond, and you have vapor coming off of it. Now notice, we had to go up to altitude to get it. That's one of the components of the pressure. Look at what has to happen to the pressure. We've got to get that pressure pretty low. Here's my pressure at triple point. And look what happens to the temperature. The temperature at triple point is way down there. It's very close to zero. So we're never going to see a triple point of water in Florida, naturally. Although I'm not sure, it's going to get pretty cold this weekend, but I don't think we're going to see a triple point. I don't think we're going to see snow. So triple point is where all three states exist simultaneously. It's not a common natural phenomenon. It's relatively unusual. Yes, this is all due to the temperature and pressure. Huh? Being low.
Wait, what about ice?
What about it?
Like you said that would ice be considered solid?
Mikey. Yes.
Because you said like we wouldn't have we wouldn't see triple point for it, but like
I suppose so. If we had a hailstorm, so you got hail on the ground that's that's vaporizing, and we've got some water still left around from rain because it rains when it hails, sure. Sure you can. We're doing great.
Yay.
Yay us. What do we call this line? I'm-
These words are new today.
Little latitude. Little latitude is all I'm asking for. The line here between solid and liquid. That is the line where we are melting and freezing.
So when that's negative, that's water. You just know that.
Yes. When that slope is negative, you know it's going to be water. That's a melt freeze.
So the top line is always that, or that's not?
The top line it should be, but hang on a minute. But just consider between a solid and a liquid. Okay.
So the SLB, those are like spaces, right?
Yes, those are the areas. So anywhere in this area is going to be a solid. Anywhere in this area is going to be a liquid. Anywhere in this area underneath is going to be a gas. And that makes sense because solids exist at very low temperature and very high pressure. Gases are going to exist at very low pressure and very high temperature. And then liquids just fall into the middle. So that's my melt freeze. What's my line between my liquid and my gas? That's vaporization and condensation.
What did you call the first line? Melting freezing.
And my third line between solid and a gas is sublimation. What's the opposite of sublimation? Deposition.
So that's when they like are all still the same state.
Those are the phase changes. So the lines between the areas represent phase changes. Okay. And the area represents the individual state of matter. The middle's where they're all three happening together. And then, of course, there's this little guy out here.
Critical point?
And what is the critical point exactly, Neha?
That's when it goes back.
That's the point that I guess the best way to say this is it can only exist as a vapor. That the temperature is so high that no matter what you do to the pressure, you can't get the intermolecular forces to take over.
And there's only one critical point.
In this graph, yes. In most graphs, yes.
The top one is not also like that.
So the top one, yes, there's critical point.
Oh, that is. Is it
There's
anything
critical point.
like the L?
Anything above that point, see how they've done the dotted line right there? Anything, so this line, kind of anything up this area over in here,
Yeah. Like that one.
huh?
Like the melting point we saw on with the other melting.
No, the second.
Yeah. Like
Hmm.
on our graph, see, there's two little guys. That little guy.
What about it?
Is there a critical point there?
No, no, no. No, critical point only exists at the end of the liquid gas line.
Okay. Not bad. Yes, I'm getting this. Except
Well-
for maybe not.
Except what?
This next problem.
Why?
I don't know, how would you ever identify, like, you need a lot of information to do that. I don't know. You also know this.
B, C, D, E, F, A, G, H, A. Consider the phase diagram given below. What phases are present at points A through H? Identify the triple point, the normal boiling point, the normal freezing point, and the critical point. Which phase is denser, solid, or liquid? So we already know. Let's start at the end. This line has a positive slope to it, so we already know that the solids, that didn't work. The solid's more dense than the liquid, right?
Yeah.
So we're doing good. A is a solid, B is a liquid, C is a gas. D is the line between solid and gas, so both of them exist. E is the triple point. F is the line between liquid and gas. G is the critical point, and H is going to be a vapor. What is what? B?
Triple point.
E, triple point, TP. So, and I leave it in here. This is problem 105, kids, out of your book. So if you just want to jot down practice problem 105, that's a pretty good one. H is already past the critical point. So anything past that critical point G, anything out here from that, sorry, I'm drawing it badly. From G up above, there's your vapor only. Nothing you can do to it can make it unvaporized. No, no. So the dotted lines, that's a great question. It did the dotted line for us at 1 atmosphere because it asked normal boiling point, normal freezing point. So if I take 1 atmosphere over to my line between solid and liquid and take it down, right there is normal boiling point. Sorry, kidding. Freezing point. And here is the line between liquid and vapor. So that's normal boiling point. Yes, freezing point is the same as melting point. Did they use melting? They used freezing. They're both perfectly fine. So it's kind of cool. At 1 atmosphere, you can see how increasing the temperature, you're going to go from a solid through a liquid and out here to a gas. Look what happens if we cut that in half. Non-normal. We go to 0.5 atmospheres. As we come across, look what happens. You can have a sublimation point, but you don't have a freezing point and you don't have a boiling point. You have no liquid phase. So graph interpretation. There will be writing on this exam. And I want good sentences, please. Okay, phase changes or phase diagrams. Pretty good. Okay, phase changes. Now everybody's comfort zone. We're only going to do phase changes for water. They're not going to be as prevalent as you would like. These are also known as heating curves. For these, you need a few different pieces of information. C of ice, C of water, and C of steam. 2.1. .18. Okay, that sounds familiar. And you see a couple of different values to this one. Sometimes you see 2.0. We'll stick with 1.8. Pretty common. And then the other two pieces we need are these guys. Delta H fuse, delta H vap. Six point oh. Now look at the units they do to you here. 40.7 kilojoules per mole. Just those are what's given. Those are on the data sheets. It ends up being 334 joules per gram and 2260 joules per gram. Those are just ballpark numbers. You'll get the 6.0 and the 40.7. So you just got to remember when you change the state of matter from solid to liquid or liquid to vapor, please be sure that you convert things to moles and do it there. But we like these. How much energy? Needed to convert. Let's take 10 grams of ice at negative 20 degrees Celsius to water at 80 degrees. You can boil it on top of Mount McKinley, which doesn't exist anymore. Pardon? 10. 10.0, sorry. I am old and very sequential, kids. You already know that. I need a roadmap. Oh, okay, I'm doing 3 steps because here's, that was bad. Here's my 0. Here's negative 10. Here's 80. So I got to do 1 step, 2 steps, 3 steps. And they have to be done separately because they all take different amounts of energy. Okay, I can do that. Just for you. I'll do it negative 20. That's fine. So step 1, ice at negative 20 to ice at 0. And I know you're thinking, how do you get ice at negative 20? But believe it or not, you can go out and buy industrial freezers that you can set them to negative 40, negative 20. It's a very common. Negative 20 is a great temperature for cell suspension, where that just kind of slows your cells down. It doesn't freeze them and kill them, but it suspends them. So negative 20 is totally doable. So delta H in that case. Oh my gosh, we're back to thermo. M, C, delta T. Yay. It's going to cost us 420 joules to do that.
But you couldn't even remember the negative signs.
We're going up, so we're okay. Just remember it's positive. We're going up endothermic. As soon as you're going up the graph, it's endo. You're coming down the graph, it's exo, and we're going to negative sign. But we're going up, so everything's going to be positive. 2, we got to melt ice at 0 degrees Celsius. Remember, at the melting point, you can have 2 states of matter, and that's okay. That's allowed. So what we got to do there, we're going to do it the right way. 10 grams, 18 grams per mole. Sorry. What was melting? 6.0. It's just a unit. Kind of just a unit hoop we got to jump through. 1 kilojoule, 1,000 joules. Munch 'em, crunch 'em. That one's going to cost us $33.40.
So what is the difference between this and what we learned in chapters ago?
Nothing. This is applying it to states of matter, solids and liquids. That's all it is. Now we got water at 0 degrees Celsius. That's a little chilly. So let's heat it up. Water at 0 to water at 80. Now we can go back to a good old fashioned MC delta T. Use our friend 4.18 joules, grams, Celsius, and we're going up 80 degrees. 33.44. Munch 'em, crunch 'em, 7104 joules. That's the total amount of energy it's going to take. Do what? Yeah, there's not much difference. We're just bringing thermodynamics back in to our phase changes. Need another? Yes. You got all your numbers. So now we're going the other direction. What temp and state and how much are present when 56.2 kilojoules is added to 20 grams of ice at negative 40 degrees Celsius. You guys know how to do this, yes? We used to know how to do this, yes?
No, I think we know. I think I know.
So here's the deal. You start out with 56,200 joules in the bank, and you just keep deducting until you run out of energy. So let's go up the graph and let's find out how much energy we need to go through each one. What do we mean by the graph? Well, it's going to be the same one And I'm sorry, I'm at the bottom of a page, so pardon my movement. Get me at the fresh page here. But we're going to do the same thing. We're going -40 over, up, and then I don't know, maybe over, maybe up. Let's see where we got to go. But we know we got to go -40 to 0 first. So let's get that energy. That's 1. So 1's going to be, I got 20 grams, 2.1 joules, grams, Celsius, going up 40 degrees. That one's going to cost us minus, that's 1680 joules. So you still got plenty of energy. 2, let's melt the ice. 20 grams, 18 grams, mole, 602 kilojoules, 1,000 joules. That one's going to cost us 6,680 joules of energy. So we've only burnt off 8,400-ish of 56,000. So we got a lot of energy left to go. 3 means we got to heat it up from 0 to 100. Take that 20 grams. Our good old friend 418 joules, grams, Celsius. We're going to cook that up 100 degrees. Still only going to cost you another 8,000, 8,360. I'm getting a little nervous, so let me see what I got left. I got 39,480 joules. So we still got plenty of juice. Step 4 is where we got to vaporize things. And this takes a lot of energy because of that specific heat. We got to go, or the heat of vape. 20 grams. Whoops. Let's do our train tracks. Ba-boom. 18 grams per mole. 40.7 kilojoules per mole. Remember, we've got about a mole. So I already know this is doomed, right? I got 20 grams, 18 grams per mole. We have over 1 mole. We need 40.7 kilojoules, and we only have 39. We know this is going to fail epically. But we'll finish it out just to make sure. We'll get the number. This is 1,000 joules. 1 kilojoule, that's going to cost us 45,200. Can't happen. So we know half the answer. What temperature are we at? We are at 100 degrees Celsius. Okay. Now what we need to do is take that 39,480 that's joules, make that 39.48 kilojoules. That's equal to M HVAP. I'm up on the high end of things. I'm vaporizing. So this is going to be M 40.7 kilojoules per mole. Which what? This is the flat phase change ones. This is this formula backwards. What I'm doing is I've got 39.48 divided by 40.7. M is equal to moles in this case that we were able to vaporize, which in this case is 0.97 moles. I'm just going to take that down here. 1 mole, 18 grams. So 17.4 of this, 17.5 is vapor. Okay. 20 minus 17.5, 2.5 grams is liquid water. And both of these are at 100 degrees Celsius. So we were able to convert most of it to vapor, but we couldn't get everything there.